Good morning, Jim Chastain with EasyPower. Today's refresher session is essentially for beginners or anyone that's starting a new project. And the intent here is to not necessarily get into any particular topic in depth, but to make sure that we have some connection with folks and their ability to kind of pick up and use the tools. So what we're looking at today, specifically some things to look at as you start to do your design, some capabilities in EasyPower that we very seldom talk about, but actually can make your project much more productive in the long run. We're going to start with a very simple system. The idea is to prove to yourself that you can get the results based upon the methodology that you're going to set up your one line with, especially in the case of a big process or a big system. And what we're going to be using is an example of both a ring and a radial system, and then talk a little bit about some of the outputs that we're trying to produce. So keep in mind when you're first trying to do a one-line diagram that you want to be able to connect between what the utility is and the ultimate load that you're trying to label, and ensure that you understand what data needs to be collected, because the thing that makes an ARC study most expensive is the fact that you need to go back out and recollect data when it was improperly collected the first time. So by going through a very simple one-line diagram that goes all the way from your utility to your final load, you can verify that the system that you're designing and the layout you're planning to go with will ultimately work for you. So along that line, I recommend that you play with the tools a little bit, especially if you're going to be doing the data collection, because you'll have a better understanding of what the tool requires, and frankly the subject regarding how the ARC flash results will ultimately mean a better and safer system and a better understanding of your system. So the database editor is used to build the model. It constructs the .dez file, and as you're building the one line, you enter the data for each element. So as I indicated, if you take time, and this may take 1 or 2 stabs at it, to basically prove out your methodology, you would be much more successful in the long run rather than have to go back and rebuild a system over. 2 types of systems, basically a radial system, which looks like a Christmas tree or a pyramid in terms of the utility being at the top and then all the distribution fanning out below it. And then a ring system where you may have redundancy and cross connects, but then below that you may have some subsystems that are more radial oriented. When we get to the reports part, in terms of compliance within FPA 70E, several times the regulations indicate that you need to start with, you need to have as your baseline an accurate one-line diagram. And so that's first and foremost what you're trying to achieve. Then beyond that, and the more accurate it is, the better the results will be that follow, which include incident energy calculations, arc flash boundaries, protective device coordination, air gap details, and arcing time. Other equipment, other reports that are vital are the short circuit report and the equipment duty report, all of which the tool produces for us. So we're going to jump into this as we start drawing the one-line diagram that the data has been collected. But as I say, you want to play with the tools ahead of time, because very frequently people will come back and say, well, do we really need all the data that's being asked for? And the answer is yes. And by trying to go through and build some trial one-line diagrams, you'll see how vital specifically cable data can be, because it directly impacts the impedance and the arcing time that's used in calculations. And then finally, the tools won't make you a power systems engineer, but it'll sure make it a heck of a lot easier to communicate by exchanging files and looking at the same data whenever you're talking about your system. So the first example I want to call up here, I refer to as my campus. Essentially, it has 2 utility feeds at 118 kV. Then around the system, there's a 13.8 kV ring that's routed to all the buildings. There are cross-connect tie breakers, and then each building has a disconnect that can isolate that particular building and then reroute energy around it if in case there's an outage or maintenance. The buildings all have 480 volt AC distribution internally, and what you're going to see here is basically a little bit of an evolving idea, and a tip of the hat to Brian Kearns of the University of Montana, because I've freely plagiarized some of his work. All right, so here's what I was just describing, where we have a ring system that starts off with the utility at 118 kV and then goes to each building in turn, and then has cross connects so that at any point in time we can isolate totally from one utility and then cross connect the energy back and forth between the plants, between the individual buildings. Now, what I'm referring to in terms of easy controls is that by putting this at my high level or at the top of the one-line diagram, I can also set up a named view. So as we come back to this, I'm going to call this my ring HV. By just clicking on this named view, it will bring me back to this zoom and pan settings so that I can come back to it as we have more complicated designs. Likewise, I want to isolate this particular drawing on a separate sheet by itself by under Drawings of the Easy Control menu, click on New Drawing, and it's telling me that it extended beyond the size of the page I had. So I'm going to go back over to my tools, pick up my drawing, pick up a larger size page, and try this again. Of course, I got to reselect. All right, so I just want to pick up this high voltage section and then put it on a separate sheet. And as I do that, I can make this look nicer and then put circles and paragraphs and annotation here describing what's going on. And then once I go back to my I actually want to rename this my high voltage ring. For lack of originality. And then we're going to take this one off. All right, now we go back to one-line diagram. Now, towards each subsequent building or each building that's downstream will be set up. In this case, I built this with the Wizard, switchgear Wizard, and it's connected at the cutout up at the building. Well, now this will be more extensive. It could be considerably more extensive. So I really want to isolate it down in an open area of the one-line diagram. So what I'm going to do is select it, zoom out a little bit, and then drag it down to this area here that I've already kind of prepared with some notation to be my area that I'm going to call Sproul Hall. And now I can go ahead and construct the rest of this radial subsystem down for as many levels and of panels and switchgear and loads as I want. Once I've done this, I can open up this cable data dialog box, and as I indicate how long this cable is, let's say it's a 500-foot run, 2 conductors per phase, 350 kcmil, so it's a pretty hefty cable run, but I'm not going to show the entire cable. And so as I do that, it ends up cleaning up the spaghetti mess that the one line can become and makes this a very easy to follow and legible one line. Now I'm going to save this as a separate drawing as I finish it. So I'll set up another sheet. I'm going to call this one Sproul. Of course, I could now have it on a smaller sheet since it's not as large, but we'll deal with that later. And so I want to call this Sproul. And then, as I go back to my one line, I want to save this particular setup view, if you will, as a named view. So if I go down to my named view and now create a new one and call this Sproul, now I'll be able to maneuver back and forth between the different settings. So now if I want to go back to my ring and then to Sproul, and then ultimately I'll be putting other buildings in other open spaces, but it'll be much neater in the long run. Now, I'm not going to take this particular the business about being simplified. So right now I have basically no loads up here on this one line yet, except for this one building. And if I go back to my home screen and look at short circuit, it's telling me I got some mistakes. Rather than worrying about filling all this in, I'm going to highlight this and deactivate it, and then just finish up this one line until I understand, or I make sure that I'm understanding what it takes to get a short circuit. Okay, so I still haven't done anything with the panel. So let's go ahead and open that up. Okay, but this actually is the point I was driving at. At this point, I've isolated my system, and the only thing that's being included in the short circuit analysis as I change the focus is that ring above, and then this one feeder leg that goes down to this panel. Now what I want to do is methodically go through and characterize the data that's required for this panel until I understand specifically how to produce arc flash labels, and consequently once I've got that level of detail included, then, and in this case you can see part of my problem is I isolated this bus. One of the things I want to get to a point that I understand all the data that's required to produce this label, and it should include this whole chain back up to the utility. And so as I unactivated this bus, you can see it cleared now to be able to do my arc flash study, so I can fault the bus or go to short circuit. So now you can see it's calculating incident energy, and at that point I go into further steps. So with that in mind, let me kind of close out of this and go back to a radial system and see if we can't take some of this discussion a little bit farther. Okay, so we have here a radial system where the utility is coming in at a single point. The 4K distribution system covers some number of switch gears or feeders. I've basically started one. Again, I want to set this up on a single page by itself. I will probably call this, for a named view, I want to call this my utility feed, which I've done. And then under drawings, I'm going to set this up as my 4.1 and 916 distribution on a single sheet by itself. And then as I construct each of the downstream switch gears, I drag it down into a free area where I want to expand it. And in this particular label, I'm going to open up and not show the entire line, so it cleans up my one-line diagram. And so I'm doing exactly what I was showing in the ring system. Here, I want to deactivate this side so I don't have a complicated system yet. And let's see if it will let me do a short circuit focus. So what I've changed now from my database editor to my short circuit focus, and apparently I have data somewhere between my panel and the utility that I can analyze. I'm going to fault all the buses. It's giving me incident energy. Let's look at the short circuit current, which seems reasonable. It's declining at each panel, which is what you'd expect. I haven't really talked about the loads on here. It looks like I just have a very small load on this particular panel and nothing else going up. In this case, we're talking about a lighting panel, so this is a step down 125 kVA. Again, IEEE indicates that this is kind of the crossover point at the level at which you expect relatively low risk of an arc flash hazard, but the tool still allows me to do calculations. And so what we have down here are 210 line-to-line panels. So I'm going to go ahead and make sure I can produce a label. So I'm gone to short circuit focus, fault the bus. Let's just worry about this one bus for starters. Fault this bus and calculate incident energy. We can see that it's very high and seems a little weird for a low voltage bus. So the next thing I want to do is look at my arc flash spreadsheet. And for that bus, because that's the only one that we've isolated, we show that the protective device that's being used to calculate its trip time is FS1. Well, if I'm not mistaken, FS1 is way back at the beginning. So let's go find it. Yep, so it's up by the utility. So the only protective device I have in play right now is this breaker. So this, again, if I were getting ready to collect data, should give me a clue that I need to be careful that I collect all the data on the trip devices that are going to be in series with this particular panel. Now, just for a real quick overview or real quick insight, when I'm in short circuit focus, I have an icon called SC Options that controls everything in terms of this particular module, both what's controlling the alert levels, which reports are being generated, what's being shown on the one-line diagram. In the case of the fault current, we're showing symmetrical kiloamps, although we could show per unit asymmetrical and max and sum of the two. And when we show remote voltage, we're showing per unit, and then we're showing just the magnitude on vectors in remote voltage. The one that's most critical for terms of arc flash calculations is the arc flash tab, and here it's showing some pretty interesting information, especially when it comes to this calculation of the panel. And before I go there, let me kind of show what I'm looking for. The icon on this panel shows that a fuse has been set up, and so if I go as far as the incoming protective device, when I go back to the database editor, open this up and look at incoming, sure enough, I have a main fuse here that's hooked up to the right cable, C8, and it's been described with some amount of trip capability, and we've done that by just the way we would set up any other fuse. In this case, it's set up for a 250 amp sized fuse. So the question is, why isn't it protecting the panel? Or is it protecting the panel? We know from the arc flash hazard sheet that it's not being calculated, and the reason it isn't is, again, part of the short circuit option selection. When we go to arc flash hazard and we look at worst case arc flash calculations, we're using a command that excludes the main breaker on any panel. In this case, it's a fuse, so we're excluding that from calculations. Several places in previous discussions we've talked about why this is the case, but essentially it goes down to whether or not that breaker or panel or protected device is isolated from the rest of the system. And you're welcome to send me an email if you got a question about it. At any rate, if I know this fuse is effective in protecting a worker when he's working on this hot bus, then I'd want to include it, and I would apply that as a result. And you can see the difference it made, albeit it's still a relatively high number, but now it's being included in the calculations for this particular panel. Some other things that are set up when we're calculating arc flash incident energy is the fact that it's looking automatically at both 100% and 85% of the arcing current, and this is per IEEE recommendations, to find the worst case time for the trip cycle. Okay, then the final note that I want to make regarding low voltage panels less than 125 kVA is that it's recommended, and based on fairly the empirical data is still relatively slim, but tests have shown over again that anything less than 250 volts has a potential for self-extinguishing an arc if it gets established in less than a couple hundred milliseconds. So one of the ways that you can deal with that as far as the tool is to change the maximum time. Let's kind of go back and look at this. Change the maximum time that's being used. If we look at this particular arc flash hazard report for this panel, we see that 210 volt bus. Now the fuse in the panel is the protective device. Here's the air gap in the panel. Here's the available fault current. Here's the fault current, or the arcing current. And here's the trip time for this fuse at this current. So the chances are that the arc would extinguish well before the fuse would actually blow. And so the tool allows us to deal with that modification and calculations with the particular checkbox I was talking about, which is if we limit the time to a half a second, because it's relatively low current, much less than 4,000 amps, and apply this, now you can see we're down in the range of this being at least a modest or an acceptable incident energy level, and consequently that may fit in within our needs of protection, but at least it's a more realistic value than we started off with several hundred calories. Okay, more information on that later. If you got any questions, by all means contact tech support or shoot me an email at jim@easypower.com. So far we've covered the ability to modify or do some trial and error runs using easy control features, and where we've set up named views that allow us to move around the one line that can be very large and complicated, but we can go to any location we want that's been saved. We've been able to create subsystem drawings, and once we're there we can insert either on the main one line or on the individual drawings the schedules. So we select a panel, we can put a schedule both on the one line or in the insert drawing, and be able to see as we add load to this particular device that it's been expanded. All right, that's pretty much our time for today. Let's see, I didn't get much into reports. We'll be picking that up on next week's refresher. But hopefully you've picked up some pointers on how to lay out your one-line diagram so that you can make it more usable and less a pile of spaghetti once you actually get into your actual system. Appreciate everyone attending. Let me see if I got a closeout slide here. By all means, make yourself be able to avail the tutorials and the examples that are on the website. There's the ability to download the free tools, and we have over 30 recorded webinars with update refreshers weekly, and then advanced seminars every week. EasyPower.com. Have a good one.